Okay, good afternoon, everyone. Good to see everyone back here for our afternoon session. So we're now going to resume with a panel on the Exascale project and how that relates to smaller scale industrial and commercial HPC systems, and the question of whether Exascale will help lift the missing middle, and which maybe one of our panelists will define, and if not, I can fill that in. So what we'll do is we'll start with Rajeev from Argonne. We'll move to Rasmus and Keven Hofstetter from Caterpillar, and then Sanjay. We'll then open things up for more general discussion, either among the panelists, questions from the audience, discussions among the audience, however things evolve. So with that, I'll let Rajeev start things off.
Okay, so the question was, or the topic of the panel is, will exascale computing help raise the missing middle? Can it, will it, how, and can it increase and broaden usage of cluster computing? So I just jotted down a few points I wanted to make. So one is I mentioned the ECP Industry Council in the morning. So it is an advisory body, and if you look at who are the members in there, it's United Technologies, Westinghouse, FedEx, Dow Chemical, Chevron, Exxon, GE, GM, Eli Lilly, Procter & Gamble, DreamWorks Animation, ANSYS, and a few others. And they're fairly high-level people in these organizations, like senior vice president or CTO-level people. And so why are they? They're quite busy in their own lives, but why are they spending time on it? Is because they want to know what is happening at the highest end of computing and what's coming in the next few years, because that will help them in their own companies. Although they may not be using machines that large or exascale systems, but there is a trickle down effect, and they may be one generation behind that in their companies, but they need to know what is coming. So they're all interested in it because it eventually reaches them, and they want to know how to prepare for it. So some of the things that come in the way, or that are sort of hindering more widespread use of HPC is one is just access to systems, and I think I've said that in the morning as well. Those of us who are at the big universities or at the national labs, we have access to systems, but beyond that, at the smaller universities or even smaller companies, it's very hard to get access to anything more than a small cluster. And even at universities or labs, time is not unlimited. You have to apply for time through a competitive program, and you may or may not get it. And even after that, there's a limited amount of time. So that itself is an issue. Another one is the training is an issue. Using these systems is not easy. Not everyone knows how to use Charm++ or any of these advanced models for using them. So training is important, and for the past 4 years, this is the 5th year, at Argonne we have been organizing a 2-week training class called the Argonne Training Program for Extreme Scale Computing. It's a 2-week residential type of program held in St. Charles, suburb of Chicago, and it's for training postdocs or early career scientists or even graduate students who are application developers mainly, and who already have some code, but this is for more advanced topics. And we have now had 4 batches of these and the 5th one this year. So there's need for more of these kinds of things. The programmability aspect of these systems is hard. They're not easy to program, and it's not easy to make them easy to program either. So all that comes in the way. The other thing is, it's maybe that not everyone has a problem that is large enough to require an exascale system. They may be happy with a petascale or a sub-petascale system as well. And in industry, they care about solving their problem, not necessarily scaling to large systems and so forth. So that's another issue. And at Supercomputing Conference, there's a tutorial every year called Parallel Computing 101, which is a very basic introduction to HPC, but it's always well attended, and there are always 100 or more attendees. And you would think that at SC, the people would already know that stuff, but no. So that's another of the training aspects. So not in any particular order. I had jotted down these thoughts, but no, I'll let someone else speak.
All right, so I guess I'll go next. All right, so I stole some slides from my presentation at Supercomputing last year. Rajeev said industry or people don't have access to these kind of systems. And that's going to be my first point of disagreement, because we actually have these kind of systems. All right, well, at some point when we get the next slide up, what you'll see is basically if we look at the amount of compute that goes into making an animated movie as a function of time, it's a curve that resembles Moore's law pretty closely. There's an exponential growth over time, and it basically shows that there's no shortage of appetite. And in order to feed that appetite, we have a data center with thousands of cores, which, all right.
There we go. Thank you.
Here's the slide showing number of compute hours for a movie going up roughly exponentially. You'll see it's a log scale on the left-hand side. So look at our data center size. That has also grown in an exponential fashion. We've been on the top less than 100 a couple of times. Lately, we haven't been running LinPack, but I'd say we're roughly top 75 at the moment, give and take. And so we've got a big system, but we're actually at a point where so far we've been able to do throughput computing. Every core can basically do a separate frame, and things are good because we've got a lot of frames. But we're getting to a point where that's no longer necessarily the solution. But if we look at a clip like this, at the moment with the current model, that took about 27 core years to actually compute this shot. Spread out over a number of cores, I think it came down to a day or so turnaround time for this shot, but still that's a pretty long time. So we'd be excited to be able to make that run faster. And so this is where I think there's a lot of potential. Also from a creative point of view, what I'm showing here is I think there's a lot of potential in using high-performance computing in general to improve productivity. You have these, what I think is a step function where if you take something that used to be a day and you turn it into, let's say, a coffee break, then all of a sudden you can start iterating a lot more on your problem. And if you take something that used to be a coffee break and you make it a minute, then you know that you're going to stay at your desk and you're going to be working on it, staying focused. And if you take something that was a minute and you make it real time, now all of a sudden you can actually interact with it and get immediate response. And that translates into significant jumps in productivity because you're no longer having to page in what you did yesterday or an hour ago. So I think there's a lot of potential. The question is, how do we actually tap into that potential? And this, well, is going to require strong scaling, and hopefully what I'd like to see out of Exascale is, can it help? I hope so. Will it help? I think that's the big unknown. And so this is where we're going to have a discussion. I think one of the critical factors is the total cost of ownership. And that's not just the hardware, it's also the software. How long does it take to develop the software? How long does it take to maintain the software? How easy is it for people to get on board with a piece of software and pick it up and run with it. A lot of what we do constantly evolves the software. It's not something where you write an application and it's golden for 10 years. We need to evolve it. And so I think a lot comes down to the tools, whether it's Charm++ or something else. How easy is it going to be? And of course, how performant is it? So I'm going to stop there.
Thank you. Okay, we'll turn it over to Keven from Caterpillar.
It's supposed to be a slide, I think, so.
Yep.
There it is.
There it is.
Okay, I've got one slide. So for those that don't know me, Keven Hofstetter from Caterpillar. My position is engineering technical steward for machine simulation. That means if you go out on a work site or construction site or on road construction and you see anything that says Caterpillar on the side of it, we're trying to figure out how do we simulate that whole system, the integration of it, figure out what the performance is, figure out what the loads are, so that we can make decisions before we ever cut iron, and when we cut iron, it's right. And so that's what we're up to doing. We're actually doing that quite a bit, and then we're also looking at where do we go in the future and vision-wise. Over the years, so I had spent a lot of time down here. NCSA was the liaison between Caterpillar and NCSA for the private sector partner for multiple years. And then in that time frame, this was back, if we go back into 2010-11 time frame, I got involved in the Council on Competitiveness. So, and they had a question about this whole missing middle or small to medium-sized enterprises, which is what the focus, I think, of the panel with the Exascale plus that. And so I had an opportunity there. There was Don Lamb, who was from Argonne National Lab. Don was on the Obama Science and Technology Transition Team, and he saw that HPC wasn't on there, and somehow we were starting to flatten out relative to other countries, and he said, we need to do something about that. He pulled together he got the Council on Competitiveness involved. There's a lady by the name of Cynthia McIntyre that worked there that headed this up, and then there were various industry people. So we had Tom Lang from Procter & Gamble, we had Richard Arthur from GE, Paul Fussell from Boeing, and myself from Caterpillar. And so we went around, and our goal in that time was actually the list, when you went down that list of individuals that are involved now with your Exascale project, we were looking at how can we, as corporate America, get more access to high-performance computing. And so that was the approach. And then we got there and we realized, you know what, the administration, they really like the small to medium-sized enterprises because that's the majority of the companies they want to go after, right? I don't remember what the number was, but there's literally hundreds and hundreds of thousands of them, and there's tens of us. Okay, so we changed our tune from, okay, we're going to go for the missing middle, and we're going to figure out how do they get access to high-performance computing, thinking, behind the scenes, we're going to wind up getting it anyway. And so we went down that path. Along with that, about that same time, Merle and myself, some others, I brought up the question and said, Merle, why don't we start thinking about what would we do if we had infinite compute power, okay? Which, again, is kind of leaning towards Exascale, right? So what would we do if we had that? And so we pondered this in our minds a little bit and actually did that back in Caterpillar as well with the group and said, well, where would we go? And so this chart, which unfortunately I pulled this out of a presentation that I gave up at Argonne for the Verify conference, and there's wording here. You can't see it. It goes right along up to seamless. It's very light. I can see it here on the screen. So I'm going to have to talk through this. But this arrow here was saying, where would we go if we had infinite compute power? And you can't, again, I will just tell you what's here. Right here it says directional. Okay, and if we think about where we were at those days, and even today, we were saying, well, we're using engineering simulation, right? So it's finite element, multibody computational fluid dynamics, those types of things, casting solidification, and so on. And so we were directionally correct down here. And we'd say, well, I can tell that design A is a little bit better than design B. I would like to say design A is going to perform at this many tons per hour, but I can't specifically do that, but I could say A is better than B. Well, that's not good enough. So where would we go next? Where we go next is say, well, I want to be quantitative or predictive. Okay, so I want to know this machine is going to perform at this productivity. Now, by the way, when you get to quantitative, that doesn't mean that I have a definitive, distinct answer if you think about the field and all these machines going out there, it's actually a probability distribution function. So it's not enough to just say my physics is better, now I can predict this particular result. It's my physics is better, and now I can tell you what the population is going to do. I've got a probability distribution function that says the probability likelihood of this thing performing at this level is this. Okay, so that's a quantitative. So it says, yeah, I need more compute power, because now I got to bring in variability, uncertainty, and I got to run a lot of simulations. And my physics has to be better, right? So, well, if that's the case, then the next thing, and again, you can't see this, but it says rapid. Okay, so I'm going from directional to being predictive to saying I need to be rapid. Well, why do I have to be rapid? Well, because I just added all that variability, uncertainty, quantification, I increased my physics, and I can't get it done otherwise. Okay, well, now there's another step we put in there, and that is, okay, I've got design A and design B, and I'm comparing A to the old one, design B. But you know what? When I think about design A, I really want to say, what if I had 5 different options, or 10, or maybe 100 different options? Now I want to compare 100 different options against my old design and come up with the optimal one. So again, that just explodes what I need for computational horsepower. And that was the fully explore. And then up here, we get to seamless. And there was a guy down in, so Oak Ridge National Lab, there's a fellow by the name of Gil Wiegand, and I don't know if some of you may have heard of him and met him. Anyway, Gil's a fascinating man. I was showing him some of this stuff one evening or afternoon down there, and he looked at it and said, it's not going to work. Really? He said, that's not going to work. He said, so I wonder, well, why not? Because this is the path I'm on. He said, you know, when you get to this integration, the seamless, and you take a solution and you put it into product development and tell the designers, here's what you're going to do. He said, they're not necessarily going to pick this thing up. And what we need to do is understand how do designers really make design decisions, and then come back and be able to integrate this whole concept of the simulation and the high performance computing, these massive numbers of simulation, integrate that into the way they're doing things so that they pick it up and it works. It has to be seamlessly integrated into the way we do product development, okay? So that was kind of the path that we were on. I had a multi-gen here. I showed this, and this was back in 2014. This is, I've got a very detailed version of this that's actually in my program that I'm driving towards. But it essentially says, okay, you know, we're heading up this thing, and we start off and we think about, well, there's experts. We need to get this right for the expert. We got to have the right physics. We got to have the realism and so on. But then this whole democratization thing comes in, and that is, I got it right for the expert, but where I really need to go is for the core analyst so they can do it, and then ultimately for the designer, and the designer being able to have applications that with standard work that they can go through all these simulations, a lot of automation, and they can very easily get their results and make their decisions. Now, if we come to small to medium-sized enterprises, where are they at? Many of those are setting back here. Okay, they're kind of at 0. And we think about the cores. We need to give them more cores. We need to give them more cores. We need to give them more cores. It was interesting that back when we were working with the Council on Competitiveness, the core cost, and if you look at smaller numbers, the core cost was heading towards a commodity, okay? And even then, these enterprises weren't necessarily picking up the modeling and simulation and doing it like they needed to do. And so there was a barrier beyond just give them more cores. And at that time, I'm not sure where it's at today. Somebody else is taking care of this now at Caterpillar. But I think the number, when you thought about license costs, the license cost was of the order about 5 to 10 times more costly than what the cores were. And so we could throw a whole lot of cores at them, and they can't afford to buy the licensing for the engineering software. So take Exascale and say, guess what? You just got 1,000 cores. You got 10,000 cores. You got 100,000 cores, and they would choke on the cost of licensing. So it's got to be the whole system, right? It's the whole system. Give them a whole lot of cores at a very low price, they still can't afford the licensing. So we have to do that. In fact, the other day I was reading an article, even this was written in, I think, just November of 16, and there was someone suggesting that in these small to medium-sized enterprises, perhaps what you should do is each analyst should keep a spreadsheet, and they could write down when they're running their jobs and what percent of utilization, so they can figure out exactly how many licenses they need and then minimize that. So I mean, even then they're saying we got to nickel and dime this thing to make sure we don't go broke. So anyway, it's going to help, but it's only one element.
Thank you, Kevin. We'll turn it over to Sanjay now.
Okay, so I thought I'll just bring the problem, define the problem a bit more first. The missing middle phrase was coined probably around Kevin's time in the competitiveness council or just before, like he said. But what it means, I just want to explain a little bit to the audience, is that technical computing is being done either on a single desktop, maybe with multiple cores, or else people are doing supercomputing, technical computing on hundreds of nodes or maybe tens of thousands of nodes. And these are typically science codes, not engineering codes. And then not enough is happening on this really 10 node, 100 node level of things. I just looked up a report from IDC, Hyperion Research now, for the 2016 year, and that kind of brings that back. The problem is kind of getting worse. They define supercomputers as things priced above $500,000, and that market grew nicely. But a supercomputer market grows by one vendor at a time. Someone just orders a big system and it jumps up. But that grew from $3 to $4 billion. And divisional segments like 250 to 500 also grew like 20% to like 2.3 billion. But the next segment, which is what we're talking about, 100K to 250K computers, declined by 20% almost, and it's only 3.1 billion size market. There's all these volumes of people buying those machines, and then the next one down also kind of declined a bit. So this is the thing. It's not getting better, but I think it is going to have to get better or going to get better. And the reason I say that is because I see some some pressures, economic pressures, pulling people that way. And you can see that going from one node to two nodes is a big thing. And then after that, going from 2 nodes to 100 nodes is a matter of money. And yes, money is important, but it's not a big obstacle. So I think we have some kind of an energy barrier or a phase transition waiting to happen. The potential, the minima is on the other side of it, but we are stuck here. And I think we have to help that phase transition happen. Once it starts happening, will be pushed along by competitive pressures. Companies trying to do, small concerns trying to do their products will realize that if they don't do these simulations, they're going to, their competition is going to do it and do better products. So that's going to push everyone to that side. And the reason I say that I'm seeing that pressure is because when I talk to ISVs that have been doing single node software, selling single node technical software to others, they are telling us that their customers are asking them for larger problems and going to a distributed memory machine rather than just ask me to buy yet another larger one node machine with hundreds of gigabytes of memory and lots and lots of chips. So I think there is a pressure from the customers towards that, and that will push things along. We have to figure out a way of lowering that barrier to make that phase transition happen. And the question is, can Exascale help? And I was wondering, after writing that, I said, how can Exascale computing even help? Can potentially even be helpful in this? And a couple of answers I could think of were that Exascale computing can just create a lot of awareness, PRs. Like people see, oh, there is this machine which can do, how many times more power than your cell phone or something like that. Popular media talking about it may increase awareness of the fact that such a thing exists. Secondly, it can improve the relevant technology. You heard in Rajeev's talk that there's a path forward, and that kind of pressure on vendors to develop new hardware that will be then broadly useful for this segment. To some extent, I do think that I'm not sure. I haven't validated that argument through any economic whatever, but maybe the NVIDIA and GPU stuff, not the GPU, but GPU, high performance GPUs, probably wouldn't have happened without for pressure from extreme scale computing. They didn't have enough of a market to justify that, I think. So that's a speculation, which I can say only in a panel. So, but those are both second-order effects, right? And so, is there a first-order effect by which exascale computing can help? And I'm not sure of that. In fact, that's probably too much of a pie in the sky for people to look at. They don't need to. We're not talking about pulling people like Rasmus towards the exascale regime. We're talking about people who are doing single desktop computing into using 8-node systems, right? And so that exascale systems are too pie in the sky for them. But maybe excess cycles that are there, crumbs literally on the exascale machines, maybe they can figure out a way of encouraging the businesses to try using mid-range software for backfill as just a part of, you have these 100 nodes lying here that will be idle until we get the next big job. Some cheap way of renting those cycles to industry. That might be one way of helping more directly. I can't think of other incentives for conversion, but maybe there could be programs like SBIR or other programs that can encourage businesses to convert their single node software ISVs to multi-node software. Another path is maybe a little bit self-serving, but it's a bait and switch idea. The idea is you make the phase transition better by taking them along a path that they keep walking on that path, they will go to multi-node solutions. And one way is, hey, write your code in Charm++. It just performs better on a single node with lots of cores. We have shown that with various cases. And you're just writing object-oriented code. You're just trying to encapsulate your data. That's all good, right? And then once they write that, then you say, well, that's running. Now, just all that you have to do is to write a pup, and you are onto a distributed memory machine. So maybe a little bit of a smoothened path to that would be helpful as well. So those are my thoughts.
Okay. So I guess at this point we'll open things up for discussion. If any of the panelists have things they want to say to each other, maybe we can start there.
I'll just add to something Sanjay said, is that if people are running on a single node, they need to take into account parallelism in some way, because the node itself is parallel already, right? And it's probably getting more so. So if we give them the tools or the technology to write their code in parallel on a node in such a way that the same tool or technology can work across nodes like Charm++, then we are helping them along that path. And similarly, many of these people don't develop codes themselves. They use some software, ISV provided software. So that software also, if it is done in a way that is parallelizable or parallel, they can use parallel MATLAB instead of the single node version of MATLAB and so on. So that's a way of getting them to multiple nodes.
So I think a lot of it comes down to pain versus gain. And I think the reality is right now there's too much gain and not enough. There's too much pain and not enough gain. Right now, for example, if we have in our data center 1,000 computers, 1,000 nodes. If we have 1,000 jobs to run there and that can saturate all those machines, then we get effectively perfect linear scaling. If we try to go through and write distributed code, then if we get 0.8 efficiency, 0.7 efficiency, then we're actually pretty happy. But the bean counters are looking at it as, you're wasting 30% of our compute resources. So that equation actually doesn't come out very favorably. You lose productivity from the programmers because they have to do something more complicated, and you lose efficiency from the actual hardware utilization. So there has to be more gain.
Yeah, I agree. And I think the point Rasmus made earlier, I underscore. It's like when you can show a quantum of, when you go tenfold faster, right, overnight to coffee break, or whatever examples he gave, then I think that makes it attractive. It's not going to be 20% faster or 3 times faster even, right? It has to be this kind of thing that was doing things that were not possible before, and we have to entice. That has to be the enticement.
So I agree with that one. And I may have ended my little introduction kind of making it sound as though, what good is Exascale going to do? And so I went back and just kind of figured a few things out. I'm not that old, but probably older than a lot of you in here. I look at just Caterpillar and what we're doing with modeling and simulation, and nearly everything we do today was impossible when I started Caterpillar. Okay, that's not that long ago. Absolutely, completely impossible. I looked at, when we started with NCSA, there was the Cray 2, if some of you have looked at that in the history books. Today, I got an old phone, by the way. It's an old phone, the Note 2, and it has about the equivalent of a Cray 2, right? I looked at, the Cray 2 was $10 million in those days. Today, I don't know what this thing was, but I kind of figured out it's something like a 28,500 times reduction in the cost of computing. Okay, and if you kind of put that into some terms that make some sense, if we had that same improvement in housing, the average house in those days, instead of costing $150,000 today, it costs about $6.20. Okay, if we had that same improvement in energy efficiency, fuel economy on our car, we'd buy a car. Today I fill my car up with fuel, and it says you got 390 miles until empty. If we had that same improvement, I would buy a new car, drive it to the gas station, put $1 of fuel in it, and it'd say you have 390,000 miles till empty. We have come a huge way, and we will continue to do that, and we absolutely need to take Exascale and drive it forward. Okay, the progress isn't going to stop. The question is, as you do the Exascale project, is that going to directly impact right now today small to medium-sized enterprises? What we found with the Council of Competitiveness thing was we need to drive that stuff forward, but then there has to be other initiatives that say, let's connect with the small to medium-sized enterprises and figure out how to get them to take advantage of what these benefits are.
Okay, so I guess Jim will start off with the audience.
Well, I just sort of had one comment. So Sanjay was talking about, if you get up to like 10 nodes, and my question is, so with what you pointed out, running on 10 nodes today is basically being one node 5 years in the future. And given the lag time and the effort in software development, are those 5 years a big enough advantage for a company like Caterpillar, where I assume you have 10-year product lines? Is that enough to drag you forward, or can you just sort of sit and wait for that one node to get faster, like in the good old days, except for parallelism, not clock speed?
I think historically what has happened is that it's been hard enough to keep up with what's happening on a single node. I know we've got plenty of code still running to this day, which is single-threaded, far from 40 or 50 cores that you can get in a machine today, or 60 on a KNL. So just keeping up with a single node has been hard enough for developers, because learning how to do parallel programming instead of serial programming is difficult, and somehow we need to get better at that. I think once you make it over the hump, like Sanjay said, then you open the floodgates, and now you can potentially scale out much further to where doing today what would otherwise take not 5 years, but 10, 20, or 30 years, that absolutely has value.
Other thoughts?
So I think it's safe to say that most people here are definitely focused on the HPC side of things, but there is an entirely different perspective to parallel computing and the high throughput systems, like the open science grid that's available through Exceed in part and things like that. Or if you're from Wisconsin, you have HT Condor. So thinking back, what Rasmus was saying is, like, if you go to supercomputing, you are teaching, there are these classes that are filled up with people who are learning essentially how to use OpenMP for the first time. And the question is, why would you teach this? And I think one of the reasons to do that is because you need to have people who can then turn around and effectively teach these skills to folks who know nothing of HPC, but could benefit from some degree of increased shared parallel programming, shared memory parallel programming, that would then be usable on systems like the OSG, where you have high throughput systems. For example, if you are a grad student in, say, economics, and your professor hands you a half a dozen Python scripts that are all serially coded, and the professor says, your thesis is now to take this serial code and do all of these calculations that are going to take you 2 years to run because it's all serial stuff. If you could apply a small amount of shared memory parallel programming skills to that and use the OSG, how much more work could you get done? And I think that that's an important component to all of this that maybe wasn't initially considered in the missing middle, but I think that bringing those folks up as well is also very important.
It certainly has a lower barrier of entry.
Any of the other panelists have anything they want to say to that? No? Okay. Everyone seems to agree. Okay. We've got another remark from Niels.
So I guess then maybe I think what I've kind of interpreted as the conclusion is parallel programming is hard. We need to make it easier for people. Is that a fair sort of one-sentence summary of kind of what?
So it's one path. That's one path. That's one of the ways in which this phase transition can happen.
Right, because it's,
But I think to the comment about if you look at the small to medium-sized enterprises, most of those companies are going to be using ISV software, right? So ease of use for the designer, the engineer in those companies means how easy is it to use that ISV software, and can I afford it, right? Lay that on top of any hardware you want, and with hardware, more is always better, as long as it's affordable.
So do you have any comments, since being in academia, I'm mainly involved in open source software. Any ideas on how to control software licensing? Since this is definitely also a consideration for us. We have a private cluster, and last January we were up. Do we want to renew our Intel license? Is it worth it for us? Because most of our codes are run on Exceed and these kinds of things. So do we need that on our private system as well? And do you have any thoughts on where maybe the direction of software models or financial models for software companies that would work both for the company but still make them affordable for small businesses to run on 1,000 nodes or something?
So maybe some others have better ideas on this. So I'm about 3 or 4 years out on this one. And with some of the ISVs we were working with, one of the models we saw was in the past was the more cores you use, the more you get charged, right? And so it didn't make any sense to. At some point, it was unaffordable. There were some models. I think Ellis Dyna, which is, let's see, what's the company? Livermore Research. They had a model where they said, you know what? If you pay us X amount of money, forget it. We don't want any more. You could run on as many cores as you want. Some of the other ones, they're looking at it and saying, well, a license costs $50,000. We'll give you a by use, and therefore each use you can pay $100, and that might be fine too. So there's all kinds of different licensing models. From the perspective of the users of the licensing, we absolutely don't want the ISV to go out of business, right? So you run them out of business by messing the license model up too badly, and then we have nothing. So they need to stay in business, but then we also have to be able to affordably. And I'm thinking Caterpillar, but now you look at the small and medium-sized enterprises, even worse for them. So how can they make some good economic decision on increasing the licensing? The ISVs will figure that type of stuff out. Ideally, if you wind up getting the volume up, so now I forget what the SMEs, there was like 400,000 of these little companies. And if you say, well, let's take some small percent of that, maybe 40,000 of them, and you start putting this software out, the volume increases the level. Now the software cost is going to come down for everyone. But it's kind of getting over that hump. How do you get over that hump?
Yeah, I think true, very true. That volume should help. The problem with licensing models is, I mean, the initial models were all like, oh, you want it for 10 cores, you want it for 100 cores, so just linearly scale the cost, the license cost. And that just is a big disincentive for people to go parallel, like a couple of you pointed out before. Now, why do ISVs do that? If they want to grow their business, they should not do that, right? And the reason for that is those markets are just small for them. People are not going to buy a large number of node licenses, and so it's kind of a chicken and egg. So it's okay, we'll just price it. If you really want it, you'll pay that price. And I think unless that phase transition happens and there is competition in that segment, and then people will start making more realistic, well-considered pricing models, combining various things that Keven talked about. And so I think that has to happen. One thing that cannot happen, I think you kind of hinted at that. If we don't want those ISVs to go out of business, basically there is a belief sometimes that open source software should solve all those problems. And the reason it does not or cannot is because it's not like Linux or something. When you have a huge number of users, then a small number of people can volunteer small percentage of their time to make it work, maybe. And in fact, then companies like IBM and so on can put some of their paid people to work on the open source software because it helps their competitiveness situation or their lawsuit situation and so on. So they prefer that. HPC is a much smaller market. We want a few people that will work on software to be well-fed, I mean, reasonably well-fed. And so at least keep them employed, right? And so we cannot get all that software done open source, although there are some good models that have kitware tries to do that, but they have a huge portfolio of various things that they do. I'm looking at this very, very carefully for myself, but my conclusion is that you cannot have software entirely developed for free within quote through open source models. And so that's one of the reasons. Otherwise, that could bring a downward pressure on all these licensing things too.
Just another comment on the open source. So suppose that we've got some program, and our programs aren't as big as Disney, and we don't use that many core hours to do 30 seconds worth of stuff. But thinking about open source, suppose we've got some program, it's a $40 million program, we have to do some computational fluid dynamics to make some design decision, and we're going to go to building some prototypes here in a couple of days or weeks or something, and all of a sudden our software is just crashing and it just won't work. We have to have support. There has to be reliability, right? And so even if it's open source, and I think Tom Lang used to talk about this with OpenFOAM, was that Procter & Gamble decided to use OpenFOAM, but they only used it after they established a support group outside of Procter & Gamble for OpenFOAM. I don't remember what the name of that company was, but there was a company, and they provided support. So anyone in the company that was using OpenFOAM, they could pick up the phone at any time and call this support line, and they would get help. We have to have things like that. It's not just put some free code in there, and you guys just kind of run like the Wild Wild West. That's not the way we do product development.
Right. I guess what I've heard as sort of a potential model maybe for this is that the software is open source, but you pay for any support. So that basically you can use it,
yeah.
But if something breaks, you're going to have to pay someone to actually help you. I don't know.
But we don't want to have to pick up the phone and discover someone after it broke.
Right.
There has to be a dedicated support.
Yes. That this would sort of fund the open source development and everything like that, and that when you engage and you say, I want to use this project, there's some contact person, and you say, okay, this is our contract, blah blah blah. We pay for support, and
it's kind of like the Red Hat model.
Right. Yeah.
Linux is open source, but they provide support.
Yeah. Just like that, I think. Yeah.
So one recent trend that I've been noticing, particularly with industries, is that so you have companies like Amazon or Google or Microsoft, which is like giving out computation units. Like for example, you can like go on AWS and get some compute units. And I'm noticing many small scale industries buying into this. So they like start getting some kind of compute units from say Amazon or Google products, and that market is working well for them, because you can notice that these companies, these kind of companies are making profits from it. So how are small and medium scale companies not benefiting from this model of where companies will like give out data center or compute units for you? I mean, they charge, but that's not very high for.
I mean, I don't think the problem is access to the compute cycles as much as it is the software that can actually take advantage of the compute cycles.
And
So
it's not Exascale.
Yeah, of course not Exascale, but the question, this is just a question. I don't have these data in front of me, but maybe some people know anecdotally which companies you have to get some software to run there, from some ISV, and that ISV has to be able to charge you something for the use of their software, even though it is in the cloud. There are models like that, but and Merle was trying to make something like that work here as well. But
But those are paid by use. And so those are the companies that are going to be using a very small number of runs, but when they really need it, they'll use it, and it's going to be a small charge, and so on. But if they need dedicated use throughout the year, then that's going to price them out.
But has the licensing models for that usage been worked out? Is there established precedent for licensing models for that, for ISVs?
Yeah, there were, I'm trying to remember this individual's name, Gray. I don't remember what his first name, anyway, Grable, Bob Grable. I don't know if you remember that name. Anyway, he had started up a company at that time when we were working with the council. Nimbus, that's right, Nimbus. And he did that very thing, work with the ISVs, got some licensing model, he provided cycles, and it was working well.
Yeah. So Jim has a remark.
So I was just wondering, is software as a service sort of a potential inroad for some of these options where the software developer provides also the ideal hardware platform, and you pay per use, you rent time on their platform, and they guarantee that it will run on that platform with whatever level of performance you're paying for, or maybe you pay for the level of performance. Is that a reasonable alternative to owning your own systems, where you build a machine, you want to build something that's generally useful for a wide variety of systems over a 5-year period until you upgrade it, versus a vendor who, okay, this is what we've got, we add things over time, we rent hardware from Amazon. Is software as a service the way that the Exascale cloud platform becomes available?
I think for smaller companies, it certainly would have a lot of appeal, also because you don't have to have a big in-house staff to do the development in the first place. For a company like Disney, I think the bigger problem is still the development tools and the programming models and figuring out how to write our own systems. But I think for the smaller places, definitely. I mean, a lot of it is still going to come down to cost.
Yeah, so that's not the main obstacle, right? That is to say, whether you get the hardware from rented from the cloud or whether you own it, as long as the software is already distributed memory parallel, then you can do all of that. I think the obstacle is converting many of these software things to that and making it affordable for people to run those.
Right, but I mean, so the chicken and egg problem is, it's like, okay, so I've taken my fluid dynamics code and I ported it so that it runs on 100 GPUs at a time, and you can go get a cup of coffee and come back and get your simulation. But who can I sell that to? Well, if I'm, renting the hardware to you along with the software, and maybe there's some backfill. Okay, it's a small integer factor more expensive, but I could provide that capability to you, and I could provide that capability to anyone who's willing to pay for it, and they don't have to buy hardware that they're only going to use on my software.
Go do it.
Well, I'll note that Rescale is actually doing exactly that. So they've licensed probably a few dozen ISV applications and just run it on their own machines. You submit a job, as input, results come back out, you write them a check, done.
So a question for Rajeev, is there examples of extreme scale computing funding in inducing industry to do things that are beneficial to, let's say, hardware vendors that are beneficial to the broad market.
Well, the funding to the hardware vendors is for specific, components or technologies at the node level or the memory level or at the interconnect level. So that does have a trickle down effect, but it'll be at the high end. So this is the vendor's high end product initially. After 2-3 years, it becomes medium end or so forth. So it eventually does benefit everyone. But the goal of this kind of funding is to accelerate things for the high end, so the high end gets it earlier than they would have otherwise.
Okay. So we've got about 5 minutes left on the panel. Okay, we've got one more question over here, and then maybe we'll ask the panelists for whatever closing remarks or thoughts they have.
I was curious if the software ecosystem is sufficient. We've talked about ISVs providing software, but are there enough ISVs providing enough software for the small businesses to actually be able to use and take advantage of?
Do you have something concrete in mind? You seem to. Is that a fact question, or you have a?
I'm just curious. Maybe what needs to happen is there needs to be more incentives to increase the number of ISVs providing software for different companies, because you need to model your problem well enough to be able to make it worth your while to go through that trouble. And the question is the software even available?
Engineering-wise, I think that there's good progress there. I think there may be some multi-physics types things and some other things that are issues, but I think it's well covered.
Yeah.
You write your own, so.
Yeah, we write our own for the most part, so I'd say where I'd like to see more software, and maybe I'm hoping to get something out of the Exascale efforts, is more on the developer tool sides, have a complete suite, an ecosystem around whatever developer languages we choose to use, whether it's Charm++ or MPI. I mean, there needs to be debuggers, profilers, and other helper tools, and having a fully fleshed out ecosystem in that sense will definitely make it easier for other developers to start picking up the skills to write applications.
Yeah, one other thing about ISVs is that an ISV that caters directly to an applications, like something that the end user uses, has a GUI, and they type their problem and get the solution, or roughly equivalent of that, has a great advantage. People start trusting it, and they are providing an end-to-end solution. But that does not help the ecosystem, like Rasmus mentioned, the program development. He talked about profilers, all that kind of stuff, as well as libraries, say Solver library or something like that. Those have it tough trying to sell. In fact, the thing about CharmWorks and so on that people told us, well, people don't like to pay for program development tools. They assume they are free. Right? And so that's a problem. Solvers, like there are great solvers in the DOE land and other places. But what our friends in that industry tell us is that, yeah, those are freely available, but without any support. And so there should be ISVs supporting those great solvers that come from research, but there is not much incentive for it for this same reason, that there is not enough money, people willing to pay for them.
Okay. So if the panelists have any last thoughts or remarks they want to make, we'll invite that, and then we'll wrap up.
So I have a comment for Rajeev, and this is something that I very, very strongly hold to. I look back back in the early '80s. We came down here. We had the Cray 2, and today thinking about it, sitting here on my phone, and you think about iPads. When I started Caterpillar, we were wondering what value the PC had in corporate America. Okay, a few people remember this. I mean, I'm not crazy, but that's what we did. Okay, think about the iPad. I don't think Apple went out and said, hey, let's go survey the grandmas and see what they want. But there's a whole lot of them that are getting a lot of advantage out of it, right? If I think about Exascale, whatever we do, we have to continue to just push the boundary on computing and push the boundary and push the boundary. Take it as far as we possibly can take it, right? Independent of whether small to medium-sized enterprise says, well, I don't know if I need that. Or whether Caterpillar says, well, I'm not sure I'm going to use it right now today, right? So absolutely don't slow down. We got to keep pushing and pushing and pushing the boundary. It probably would make sense if we had some other initiatives that say, well, now how are we going to take what we're developing and get it into the hands of the people that need to use it?
I can pretty much only agree with that. I think we have some real challenges ahead of us in terms of getting over the hump, but I see a lot of potential on the other side of the hump. So let's make it happen.
Yeah, I'd say the changes in hardware that the parallelism is so easily available even on your cell phone are kind of forcing people to think parallel or program in parallel. So I think it'll naturally happen to some extent. But we have to help them with the distributed memory part.
So a couple of thoughts. One is that, well, there are ways in which exascale computing can help the middle scale. One is that software applications, whatever software tuned for exascale, for large scale machines, can very easily scale to 100 nodes, right? So that makes it that definitely helps the 100 node scenario because you have already scaled it to much larger machines. The other thing is the indirect, other than the indirect factors that I mentioned earlier, where how exascale helps, there is not much exascale is beyond those. Exascale is not going to help the middle much. However, the phase transition for the middle to go from to the middle will happen, and it will happen because of intrinsic economic factors pulling people that way.
Okay, thank you to our panelists. Let's give them a round of applause and go to the break.